Let's talk about weight in an elevator. We'll start by discussing the equivalence principle, and then we'll determine the weight in an accelerating elevator and solve an example problem. The equivalence principle states that gravitational and inertial forces are fundamentally the same. What this means, in essence, is that if you were sitting in a rocket, so you just woke up sitting in a chair in a rocket, you couldn't really tell if the rocket was sitting still on Earth or accelerating in deep space at 9.8 meters per second squared. The acceleration caused by the gravitational force or by the force of, say, a thrusting rocket is essentially the same thing. Now we'll talk about weight in an elevator. We'll start by looking at an elevator that's at rest. Consider a massive block sitting on a scale. The gravitational force from the Earth is pulling down on the block. The normal force from the scale is pushing up on the block. The reading that you see on the scale is really reading the normal force on the scale. Since your force pushing down on the scale is the same as the force of the scale pushing up on you, that normal force that the scale is reading is the same as your weight. In the case of a rest frame, the weight equals the gravitational force, which on the surface of the Earth would be mg. If the elevator is accelerating upward, then when we draw a free body diagram, to get the acceleration pointing upward, we need to have a normal force that is larger than the gravitational force. Remember, the gravitational force hasn't changed, the mass hasn't changed, and the mass of the planet hasn't changed, but the normal force is going to be larger. Think about it this way. Think about what it feels like if you're in an elevator and it suddenly starts to go upward. It feels like you're being pushed down into the floor. You're pushing down harder on the scale. That means that the weight that the scale is reading is going to be larger than it was before. The weight in an accelerating upward elevator is greater than mg. To illustrate this, let's solve an example problem. We'll find the weight of a 77 kilogram person in an elevator that's accelerating upward at 1.1 meters per second squared. We'll start by drawing a diagram and listing our assumptions. Then we'll define known and unknown variables, write the general equation and specify it for our system, solve symbolically in terms of given variables before inserting any numbers, and then we'll analyze the result. Here's our free body diagram. As before, we have that the normal force is larger than the gravitational force to give acceleration that's in the upward direction. Our assumptions are that we are close to the surface of the Earth. The Earth is a spherically symmetric body that has gravitational acceleration of 9.81 meters per second squared. We're also assuming that we are a spherically symmetric object. The known variables are that the mass is 77 kilograms, acceleration 1.1 meters per second squared, little g is 9.81 meters per second squared, and we want the weight. Our general equation is sum of forces equals ma. This is a one-dimensional problem, so we'll solve it as a scalar problem. We start by listing the forces from our free body diagram. The sum of forces equals ma equals the normal force minus the gravitational force. We've defined upward as being the y direction because our acceleration is upward. As we discussed, the normal force is actually a measure of the weight. And here, the gravitational force is just mg because we're close to the surface of the Earth. We rearrange our equation to solve for the weight. We get that the weight equals the mass times the sum of g plus a. Inserting our numbers for the variables, we get that the weight equals 77 kilograms times quantity 9.81 meters per second squared plus 1.1 meters per second squared, which equals 840 newtons. Let's do a bit of analysis. First of all, we see that the units make sense. They work out to be kilogram meters per second squared, which is newtons, like we'd want for a force. We look at the weight at rest. That would be 77 kilograms times 9.81 meters per second squared, which would be 755 newtons, or 170 pounds. The accelerated weight, converting into pounds, would be 190 pounds. This makes sense. We expect it to be somewhat more. What this really means is that if your elevator is accelerating upward at 1.1 meters per second squared, you're pushing down on the scale, so your effective weight is 190 pounds. You're pushing down on the scale with an extra 20 pounds of force. That may seem like a lot, but 1.1 meters per second squared is a pretty high acceleration. In summary, we learned that the equivalence principle states that gravitational force is fundamentally equivalent to inertial force. Weight is equal to the normal force exerted on a scale, and weight is higher in an elevator accelerating upward, which we found by working a simple problem.